Hi, I'm Felipe Lopez Mantilla, and this is my thesis project, Xylem, for the Master of Science in Data Science and AI for the Creative Industries at the University of the Arts London in the Creative Computing Institute. In this project, we'll be exploring how biomimicry learning principles from nature can guide agentic AI to optimize step-by-step tasks in 3D simulation for dynamic environments. Moving forward, what is biomimicry? So biomimicry is principled emulation, not copying from nature itself, but how it works, to observe, abstract, translate, emulate, and iterate by using evolutionary strategies that have been adapted from the start of life itself, and how these adaptations that are found in nature can provide some feedback, efficiency, and cooperation when tested against current solutions. So, for AI, this means a contextual local rule that can be scalable and and allows for adaptation and coordination for decision making in this case. And continuing on it, my research question is how can biomimetic principles be integrated with agentic AI in a 3D dynamic environment to simulate human-centered task systems. So for this, we have selected three different biomimicry layers, which are the ants colonies, the Physarum fungi example, and the river Steiner theory. That it's gonna be compared against the Dijkstra algorithm and a human AI LLM with the same, with parameters similar to the ones from the biomimetic system, but based on human activity and human progression. But what is the actual problem here? Real workflows lose time in staging and hands-off, and that's not just for distance. We can start thinking of a of the problem of the traveler agent that's trying to solve moving piece A to B, from B to C, and from C to D, and how it's not only about the movement itself, but about the congestion, recrossings, idling stages, and how real life conditions affect the way that we transport and that we move around into solving these problems. So we have the retrieving, the staging, the assemble, and the delivery, and that's what we're going to be aiming to optimize. So our proxy itself is a sandwich making process on a pipeline. What I mean by that is the task order that we have on our system is going to be delivering a sequence that our agent setup is going to be preparing for the agent carriers to deliver onto their final part. These ones are going to be working underneath a layer of the selected layer, which I'm going to be presenting in the next slide. These agents themselves work underneath an operationalized policies, which are the rule, LM, and the hybrid ones. Rule are deterministic heuristics that have been set from the literature reviews and from talking with experts on each field on how the movement should be coordinated within the different layers. The LM then it's able to set up LLM. It's able to set up a set of rule sets that it's gonna be used in case, let's say, it's an ant's Neivamyrmex ant, apart from that ant colony planner, and the rule set that it's gonna be following. And the hybrid is gonna be determining. It's the part that determines whether or not to use one or the other based on what's the best condition in comparison for the exact pattern that's happening at the moment. It's all based on policies, but and no randomness when it comes to selecting the layer, the sublayering, and the mode that it is running on. So, what are the sub layers, and how does this look on a hierarchical standpoint? So, each family pairs with a biomimicry sublayer that biases routing, staging, and yielding. Ants have the Neivamyrmex, Atta, and Dinoponera sublayers. The Physarum has a network, a dispersion, and a peristaltic sublayer, and the Steiner river has an active, passive, and mixed policies. And all of these work together in order to deliver the best possible result based on the rule sets that have been given to them. In terms of the system architecture of the system, we're using a Unity 6 running physics and Neivamyrmex through a decision bridge, custom made code that sends a compact state to a flash service and then continues to give the rule sets and the instructions to Mistral and then back to Unity in order for the agents to move. It gives, for example, if let's say we have our agent setups with our identities and all that, it all goes to the planner and then it gives the staging points where to go, and the server is the one that connects the HTTP request in order for everything in the system to be connected and working around it. Our hypotheses are that the first one, it's on efficiency mostly. Biomimicry should reduce time redundancies versus non-biomimetic human baselines. The second one is our rule-guided biomimicry enhances adaptability. Our expectation is that hybrid LM and rule sets adapt better to the altered staging points and density stages than a single mode agent. And that social biomimicry outperforms when paired with or compared with the other layers. So the ant colony would be a better coordinator and a better solution maker than the river and the Physarum ones. Our objectives is we aim to find a consistently outperforming layer and compare time, distance, idle time, and other staging issues to test adaptability in social and non-social layers against the human and the Dijkstra algorithm. Our temporal savings are not only in movement but also in staging setup, and we'll be comparing the LLM, the hybrid, and the trade-off parts of it, and the rule sets as well. During the development, we built it in Unity 6, basing it on Neivamyrmex for the recognition of the area, then a decision bridging that works towards the backend that we're running on Python 3.11, running Flask, through also Olama and Mistral LLMs on this Flask server that creates inside this HTTP JSON file that's then converted into CSVs that we'll be seeing the results on them later on. And here is a view on how the implementation itself works. We can see that the agents, the blue agents, are setting up the project itself. Here we can see the red one, which is the setup agent, putting the tasks, each of them in place so that the agent carriers can then continue on seeing this. So this is another sense of the retrieve, stage, handoff, delivered, and where the biomimicry policies show coordination and not just path length calculation. So based on this, the results and outputs, the top median versus the Dijkstra, it's 20, which is 20.75 seconds. We have the closest one, that was the ants rule Atta at just at a really close one with Dijkstra, just 0.2 seconds later. Then we have our first hybrid, which is Dispersion at 0.315 seconds. Then we go into the Steiner hybrid, and all of the ones that appear here were the ones that were able to beat the human rule sets, LLMs and hybrids, and go really close to the Dijkstra algorithm. This is all having into consideration the 9 policies and the different rule, LLM, and hybrid setups that have been added. In here we can see each of the ones that we've compared. So the ANS Neivamyrmex hybrid version has a median of 21.405 seconds, which has a delta of plus 0.655, and it's faster than the human rule set and faster than all of the other human layerings. We can see the 3D spatial against time view on it, and how its acceleration changed depending on the layer and the sublayering that we've chosen. That can also be seen in the latter ones, where you can see different decision making on curves and more spatial aware spaces. This one has a higher difference within the when compared to the Dijkstra. However, it also has like a different standpoint on how the network reroutes and cleaning and makes like the blockages be more robust. And at last in this comparison we'll have the Steiner river hybrid active, which has a lower delta on it and also has one of the best runs when compared, which is an 18.4, though this is not part of the median one, but rather the like a peak result that it had. And it also beats the Dijkstra in this case, but we're only gonna be considering the median ones. So in conclusion, our first hypothesis is supported as the multiple biomimicry policies beat the human medians. The Atta rule comes closest to Dijkstra. Our second hypothesis holds in level 1 as well. Hybrids balance the rules stability with the LLM flexibility, while also keeping up with the speed that the rule set provides. And the H3 for our third hypothesis is visible as the social strategies reduce the recrossings and improve on handoffs. We've met our objectives as well, as we identified strong layers comparing efficiency, testing and adaptability connecting to human-computer interaction when we do the comparison on it. And our next steps would be to scale. So being able to look for denser scenes, create second levels, train specific models and agents so that the intrinsic time is not as big, and to be able to pilot in logistic and agricultural context. And that would be it. You can find links to the GitHub repository to do a run for yourself, and the results folder on all the results that we just saw before. Thank you very much, and hope you have a great day.